Hi everybody. In today's lecture, I'd like to talk to you about capacitors in circuits. So first of all, oftentimes it really helps, instead of looking at a real circuit, to have a simplified view of the circuit, because if you've ever tried to wire a circuit yourself, then you know that after a while they kind of start looking like a hot mess. And so sometimes it's nice to have a simpler representation. And so what we do is we have certain symbols that we use for different circuit elements. Now, we just have straight lines that are used to represent the wires in a circuit, okay? So anything coming off these circuit symbols is meant to represent a wire. And usually in circuits, we assume that all our wires are perfectly conducting and have no resistance or capacitance to them, okay? Now, for the circuit symbols, we'll be going over in various lectures the different symbols that are used, but for today's lecture, the ones that you need to know are shown here, and it's the capacitor, okay? Today we're dealing with capacitors, and capacitors are represented by two parallel lines that are the same length, okay, shown here. They're not always going to be in blue, that's just meant to highlight what they look like right here. We're also going to deal with batteries. Batteries are also two parallel lines, but for a battery, one of the lines is shorter than the other. The shorter line represents the ground of the battery, and then the longer line represents the positive terminal of the battery. And we also have switches. Now, switches are represented usually by little circles on the end of wires with a line drawn in between the two circles. If the line does not connect the two circles, then that's an open switch, which would of course mean there's no current flowing in that circuit. And then if you have a closed switch, then current flows in the circuit, and that means that the line should be drawn connecting the two circles, which are meant to represent the terminals of the switch, by the way the circles are. Now, there's two main ways that you can hook things up in a circuit, and that's in parallel or in series, okay? So when we have a parallel branch in a circuit, what we usually do and why we call it parallel is because when we draw the schematic of the circuit, the branches are represented by parallel lines, okay? So what we have here is we have a battery, and from the positive terminal of the battery you have a wire that leads out, and then that splits off, okay? Now, the bottom here runs through capacitor C2, and then the top wire runs through capacitor C1. And C1 and C2 here are in parallel branches. So basically, parallel is when it splits off, branches out, and then comes back together, okay? So these two are in parallel. Now let's talk about what would happen if you had this simple circuit represented here with just this battery and these two parallel capacitors. What would happen is, of course, that we would have an unbroken line from the positive terminal of the battery to the left plates of each capacitor as shown here. Now what's going to happen is that that is going to have the left plate of each capacitor with a positive charge. And then there's an unbroken line from the negative terminal of the battery here to the plates on the right, and that means that that branch or that side of the capacitor will be negatively charged, okay? And that's because in this you're assuming that you have these free electrons that are moving around within the circuit. Once the switch is closed and it's hooked up to the battery, there will be, until the circuit comes to equilibrium here, which is a very brief amount of time as there's no load on this circuit, there's going to be a flow established by the electric field from this voltage that's set up. And that transfers electrons from the plates on the left, okay? So in other words, that battery is going to cause a force from the electric field that's going to move the electrons that are on that left plate originally away from the plate and causing it to flow away. And then of course that induces a positive charge in the plate, which attracts electrons that are drawn from the negative terminal of the battery, and the electrons build up on that plate on the right, okay? Now, the flow of charges is going to cease when the voltage across the capacitors equals the voltage supplied from the battery, okay? That's when you'll have a net voltage of 0, which means the electric field goes to 0 within the circuit, and current stops to flow. So the potential difference across those two capacitors is going to be the same, and that's because the battery forces it to be. As you can see in this simple circuit, you have the battery terminals directly hooked to the left and the right side of the capacitor plates. And so that means that battery is holding, once it comes to equilibrium, the battery is holding those capacitors at that voltage, okay? So each capacitor sees the same voltage from the battery because it's forced to do so, right? Because it's directly hooked up. Now, that is true for this simple little circuit, but it's also true in general for parallel lines in a circuit. The voltage drop across parallel branches in a circuit is going to be the same. Now, for this simple circuit, that voltage drop across the parallel branches will also be the voltage drop held by the battery. So we can say here, using phi to symbolize our voltage, delta phi from the battery is going to equal to delta phi 1, which is equal to delta phi 2, okay? So the voltages are the same across those parallel branches. Now, the capacitors are going to reach their maximum charge when the flow of charge ceases. That total charge is going to equal to the sum of the charges on each capacitor. So we could say that Q, which big Q here, which is the charge on the whole circuit, is equal to Q1 plus Q2, where Q1 and Q2 are the charges built up on capacitor 1 and 2 respectively. We can use our equation for the capacitance here. Remember that for a capacitor, C is equal to Q over delta phi, where Q and delta phi are the charge and voltage for the capacitor respectively. So rearranging that equation, Q is equal to C delta phi. So our total charge for the circuit, Q, big Q, is equal to the equivalent capacitance for that circuit, CEQ, times the voltage from the battery, delta phi, right? Now, because the sum of those two charges sums together, Q1 plus Q2, then we can sub in the equations for charge Q1 and charge Q2 from our battery respectively. So that will be Q1 is equal to C1 times delta phi 1, and Q2 is equal to, I'm sorry, that's supposed to be C2 times delta phi 2. All right? So now if we know that the voltages from the battery and from the parallel branches, those are all the same, because we said that voltage drops across parallel branches are the same, then we can cancel that delta phi 1, and delta phi 2 out, okay? And that just leaves us the equation for the equivalent capacitance here, which is that C equivalent, CEQ, is equal to C1 plus C2. Now, I derived this equation for just this simple little circuit. However, the fundamental principles are the same no matter how many parallel branches that you might have. And so when you have the equivalent capacitance for parallel branches, you just sum up the capacitance of each branch. So CEQ would be equal to C1 plus C2 plus C3 over how many parallel branches you might have. So the idea behind an equivalent capacitance is that if you have a more complicated circuit, right, then you can represent the capacitance for the more complicated circuit with just one capacitor. So in other words, for our little circuit that we showed here, C1 and C2 could be combined, in effect, to be replaced by one capacitor that has the equivalent capacitance of C1 plus C2 for parallel branches. To summarize, the equivalent capacitance for capacitors in parallel is just the sum of the capacitance of each branch. So the equivalent capacitance for capacitors in parallel would be C1 plus C2 plus C3. And that makes it, of course, greater than the capacitance of any one of the capacitors individually. Now let's talk about how you would deal with an equivalent capacitance if you had a different configuration. So here, instead of hooking them up in parallel, we've got them hooked up in series. In other words, one after the other after the other, okay? So let's talk about what would happen physically here. You've got the positive terminal of your battery hooked up to this leftmost plate in this series, okay? Now I'm going to refer to them going left to right as plate 1, 2, 3, and 4 here, okay? So plate 1 is directly connected to the positive terminal of our battery. Now, as we saw from the previous discussion, that's going to cause a positive charge to build up on that leftmost plate as electrons are transferred away from the plate due to the electric field that's briefly established in the circuit before it comes to equilibrium, okay? So I'm going to get a charge plus Q built up here on this leftmost plate. Now, if you think about it, there's no direct electrical connection between the left plate, plate 1, and the next plate, plate 2. And plate 3 is not electrically connected directly. There's no wire, in other words, that connects plate 3 to plate 4. So that means that plate 2 and plate 3 are kind of their own little system here, right? So originally, of course, everything is neutrally charged. But then what happens is there's this positive charge plus Q that builds up on plate 1 on this leftmost plate. Well, what's going to happen then is that the electrons in this little isolated circuit here between plate 2 and plate 3, they're going to be attracted to that positive charge. So the electrons are going to move away from wherever else they are in the circuit and build up on this plate 2 right here. And they're going to build up until there's an equal and opposite charge on plate 2. When that happens, that leaves an absence of charge here on plate 3. And so plate 3 is going to get plus Q built up on it because it gave its electrons to plate 2. Now, this plate 4 here is going to see this positive charge, and it can draw electrons from the battery. So electrons are going to be transferred from this negative terminal of the battery to build up on plate 4 until it's equal and opposite to plate 3. So that means that for plates 1 through 4 respectively, you're going to have plus Q, plus Q, and minus Q building up on the plates. All right, so that's physically what's happening in this circuit. What that means is that the amount of charge stored on each capacitor in series is going to be the same. So the charge for capacitors in series is equal. Okay? Now we can use this idea that the charge for capacitors in series is equal, right, to figure out what the equivalent capacitance for this circuit will be. Okay? Q1 is equal to Q2 is equal to Q. Now, unlike in our previous example for parallel branches, the voltage drop across capacitors in series does not necessarily have to be the same, okay? What does have to be true, though, is that the voltage drop, let's say that it's just this simple circuit that we have here. We have a battery hooked up to it, and we have these two capacitors, right? And they're going to get some voltage on each of them, voltage 1 and voltage 2. Now, it is true that the battery is forcing the circuit to hold a certain total amount of voltage drop. And so that means that these two respective voltages, when added together, must equal the total voltage drop supplied by that battery. So your potential differences are going to add up to a battery voltage. Your total battery's voltage drop is going to equal to the voltage drop across each one of your capacitors in turn in that simple little circuit. So delta phi total from the battery will equal delta phi 1 plus delta phi 2. Now, we can rearrange our equation for the capacitance, right, and solve for the voltage. If we do that, then the voltage will be equal to the charge divided by the capacitance. So we've got our total voltage from the battery, delta phi. That's going to equal to the total charge stored in the circuit divided by the equivalent capacitance for the entire circuit, okay? So Q total over the equivalent capacitance will be equal to the voltage from the battery. Now that's going to equal to delta phi 1 plus delta phi 2. Yet again, we're going to sub in for the equations for the capacitance here for delta phi 1 and delta phi 2. We're going to use that equation for the capacitance and sub in. So delta phi 1 is Q1 over C1 and delta phi 2 is Q2 over C2. But they add up, so we end up with the equation Q total over C equivalent is equal to Q1 over C1 plus Q2 over C2. Now we already said that those charges for the capacitors in series are all the same. So that means that Q total, Q1, and Q2 are equal, and we can cancel them out of this equation. That leaves us with just the equation for the equivalent capacitance. 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2, and that would do it for this simple circuit, but if you had more capacitors in series, it would just keep going. 1 over C3 plus 1 over C4, so on and so forth, okay? So this is how you find the equivalent capacitance for capacitors in series. You add the reciprocals and then take the reciprocal of that. That makes the equivalent capacitance of a series combo less than any individual capacitor in the combo. All right, so how do we use these two ideas, the equations for the capacitance in parallel and the capacitance in series? How do we use those two equations to find the equivalent capacitance for some hot massive capacitors? All right, so let's look at this kind of crazy configuration of capacitors right here and break it down. So between points A and B in this circuit, we've got 6 capacitors. Looking at this, there's 2 main parallel branches, right? And those 2 main parallel branches have a 4, and then a 1 and a 3 in parallel on top. And then on the bottom, they have a 6 and a 2 in parallel, which is then in series with an 8. All right, so what would you do? Well, what you do in any of these situations is you break it into little manageable chunks. You find the equivalent capacitance of the chunk, and then you use that to continue on in your journey to find the equivalent capacitance of the whole. So what I would do is I would first look at this and say, okay, I can find the equivalent capacitance for these little parallel bits right here, right? This little parallel chunk, where I have the 1 and the 3 in parallel. Now for parallel capacitors, I just add them up. So the equivalent capacitance for this little parallel branch with the 1 and the 3 microfarad capacitor in it would be 4 microfarads. So I can sum this 1 and 3, making a 4, and then sub in that equivalent capacitor for the parallel right there. I can do the same thing on the bottom. I've got a 6 and a 2 in parallel, right? So that means 6 plus 2 is 8. I can draw an equivalent capacitor of an 8 microfarad capacitor right there, okay? So now I have a parallel branch, 2 4s are on the top branch, and 2 8s are on the bottom branch. Well, now I can find for this top branch the equivalent capacitance. This is a 4 and a 4 in series. For series capacitors, I add the reciprocals. So that's 1/4 plus 1/4. 1/4 plus 1/4 is 2/4. Now to find the equivalent capacitance, I then need to take the reciprocal of that. So 2/4, doing the inverse, is 4/2. And that makes the top branch have a 2 microfarad capacitor subbed in there. Okay. I can repeat this process for the bottom branch. I have 2 8s in series. That's 1/8 plus 1/8, which is 2 8s. Taking the reciprocal of 2 8s, I get 8/2, which is 4. So that means that the bottom parallel branch is a 4 microfarad capacitor, right, equivalently. Now I have a 2 and a 4 in parallel with one another. For parallel branches, I sum it up to find the equivalent capacitance. 2 plus 4 is 6. So that means that my final equivalent capacitance, where I can sub one capacitor in to represent all 6 of these capacitors, that gives me 6 microfarads. Okay? So that's your strategy. You take these little chunks, find the equivalent capacitance of the chunk, and then just keep going until you only end up with 1 at the end. And that's how you find your equivalent capacitance. That's the strategy. All right, now there's another kind of equivalent capacitance type problem for circuits, okay? So if you just have a battery and a bunch of capacitors, sometimes they'll ask you to find the charge stored and the voltage dropped across each capacitor in the circuit once the switch closes, okay? So let's look at this little example problem. Here we have a 9-volt battery hooked up to a 5 and a 2 microfarad capacitor in series, and then that's in series with a parallel branch, which has a 10 and a 6 microfarad capacitor in each one of the parallel branches, okay? So the problem says, find the charge stored and the voltage dropped across each capacitor in the circuit below once the switch closes. All right. Well, there's a certain strategy that you use to approach these types of problems. Step number 1 in this is always to find the equivalent capacitance of the whole circuit, right? Once you find the equivalent capacitance of the whole circuit, then you find the charge stored in the circuit. The charge stored in the circuit will be the same as the charge for any of the capacitors that are directly connected in series to the battery. Once you do that, you can find the charge, right? Using the charge, you can find the voltage dropped across each capacitor that's in series. Using the voltage drop for any capacitor in series, you can then find the voltage drop across the parallel branch. Once you find the voltage drop, you can use that to find the charge. So that's kind of the strategy for any one of these problems, all right? So let's go through this process for this problem. So to find the equivalent capacitance, we take it in chunks. So we have this one chunk where we have this parallel branch right here with the 10 and the 6 in it. So we would add those two together. 10 plus 6 is 16, and that means that the equivalent capacitance for the parallel branch, which I've called C para here, is equal to 16 microfarads. So now I have a 5, a 2, and then an equivalent 16 microfarad capacitor in series with one another. To find the equivalent capacitance for capacitors in series, I add the reciprocals. So my total capacitance for the circuit, 1 over C total, would equal to 1 over 5 plus 1 over 2 plus 1 over 16. Okay? So you could add those up in your calculator, right? And then use that to find the reciprocal of the total capacitance and then take the inverse of that. So I've just represented that here. The equivalent capacitance for these series capacitors would be 1.311 microfarads. My usual strategy in these kinds of problems is to keep a lot of digits and then round at the end. Okay, so that's usually what I do. So I'm keeping this 1.311 for a little while. Okay, now this is the total or equivalent capacitance for the circuit. Once I have the total capacitance for the circuit, I can use that to find the total charge stored. So I'm going to use the voltage from my battery. That's going to be my total voltage drop from my circuit. And C total will equal to Q total over the voltage drop from the battery. So 1.311 microfarads is equal to Q total divided by 9 volts, which is my battery voltage. Cross multiplying, I can find the total charge stored in the circuit, Q total, which is 11.8 microcoulombs. Okay. Now, this charge, 11.8 microcoulombs, will be the same as the 5 microfarad capacitor's charge and the 2 microfarad capacitor's charge because they're in series with the battery. So Q5, Q2, those are both 11.8 microcoulombs. All right? Next, using that Q5 and Q2 11.8 microcoulombs, I can use my equation for the capacitance, C is equal to Q over delta P, and find the voltage drop across each one of those capacitors individually. So 5 microfarads is equal to 11.8 microcoulombs divided by the voltage drop across the 5 microfarad capacitor, delta P5. Cross multiplying, I can find the voltage drop across that 5 microfarad capacitor. It's 2.36 volts. I can do the same process with the 2 microfarad capacitor. 2 microfarads is 11.8 microcoulombs divided by delta V2. Cross multiplying, I end up with a voltage drop for the 2 microfarad capacitor of 5.9 volts. Okay. Now, I found the voltage drops for the 5 and the 2 microfarads. As we talked about, when you have components in series, the voltage drops add up. Okay. Now, the voltage drop should be the same across the 10 and the 6. They're in parallel. But whatever the voltage drop is for the 5, plus whatever the voltage drop is for the 2, plus the voltage drop for the parallel branch, that has to sum to 9 because that's what the total voltage drop for the circuit will be because of the battery. So that means that I can take my 9 volts and subtract off the voltage drops from the 5 and the 2 microfarad capacitors and then find the voltage drop for the parallel branch. So 9 volts minus 2.36 volts minus 5.9 volts is equal to 0.74 volts. That's the voltage drop for my parallel branch, right? That's going to be the same as the voltage drop for the 10 and the 6. So I can use this 0.74 volts for the parallel branches and find the charge stored on the 10 and the 6 microfarad capacitors using my equation for capacitance. 10 microfarads will be equal to the charge stored on the 10 microfarad capacitor, which I call here Q10, divided by 0.74 volts. Cross multiplying, I can find the charge stored on the 10, Q10, it's 7.4 microcoulombs. I can repeat that process for the 6 microfarad capacitor. 6 microfarads is equal to Q6 divided by 0.74 volts, and that gives me Q6 is 4.4 microcoulombs. And that's it. We're done. We found the charge stored and the voltage drop for each capacitor in our circuit, and that was what the problem asked us to do. You can also, of course, once you've got the charge and the voltage for a capacitor, You could also find the energy stored, right, using our equation for potential energy for capacitors, right? 1/2 CV squared or Cp squared, 1/2 the capacitance times the voltage on the capacitor squared is the potential energy. Using the equation for capacitance, you could sub in, right? So 1/2 Q squared over C or whatever else, right? There's 3 equations that we have for the energy that's stored on a capacitor. All right, that's it. I hope you understood that. Remember that if this gets a little fast for you at any point, this is a video, you can pause me, okay? So with that, I'll see you around. Hope you enjoyed it. I'll see you in class.